Hello, this is a short tutorial on using the software in Lab 1. First of all, comments are very important, and the first two lines has a space for a comment, but make sure you change the date and your name here. Secondly, these comments are for a whole line. It starts off with a slash and asterisk and ends with an asterisk and slash. If you just want to add it to the end of a line, then the way to do that is put a double slash and then continue your comment. If you don't see the serial monitor, like in this case here, then what you must do is come up to the top, click on serial monitor, and then you will see that screen. You can turn it on and off here. This is the output to check for errors, but the serial monitor is clicked on over here. On the right hand side, there are three icons here. This first one is to toggle the auto scroll. And I find it best to leave auto scroll on, but notice down here this scroll bar stays down at the very bottom, and the data up here is the latest data that's being refreshed. If you want to turn that off, you would click on this button, and then you'll see the auto scroll button move upwards, and now you have a choice of scrolling through the very first line of data or the most recent line of data. But it'll go away, so you're not seeing the most recent data. So click on the auto scroll, and that way you will see the update continuously. The second one is a date timestamp. So it puts the date, time, sorry, not the date, but the time and the number of milliseconds right over here. Sometimes it's worthwhile turning it on, but most of the time keep it off. And then the last one is if you want to clear the screen. Okay. And with auto scroll turned on, it'll just continue updating live the data down at the bottom. If you want to change the size of the font in your program or in the output, go up to File, Preferences, and there are two choices. You can make the editor font bigger or smaller by changing this value and saying OK. So you can see it's a little bit bigger here, and you can also go back. And if I want to make the output a little bigger or smaller, you would change this number, put it in auto, and bring it back down. I think auto will change both, but let's say I want the output to be just a bit bigger. I'll do this, and now the output is bigger. Okay, let's turn that off. Just go back to a smaller size. Here we'll change this back to 100, and this is typically 14. Okay, but in our case we want it to be a little bit bigger, so let's go to Preferences and maybe make this 140. Okay, so that's a good size to read the information. This is an example of the circuit used in lab number 1. It has two LEDs, a push button, a low pass filter, and a 5K resistor. Let's have a look at the program code. So on lines 3 and 4, they are there to set up the green LED and the red LED in hardware. And so if you hover over a variable name, it will actually show you the pin number. So the pin number is 8 in that case. And we're setting up the green LED to be on pin 8, the red LED on 9, the push button on 3. The other thing that's important to do is you have to set up the supply voltage, because it's going to differ from USB connection to USB connection. Kind of depends on your computer. In my case, it was 4.6 volts, so that's the value that I used. And a floating point number has a decimal value, whereas integers don't. So the second thing that you want to do is in your setup code, you want to tell the system that you're operating at 9600 bits per second. So I have it written in my program, plus in your Arduino IDE, you have to make sure this is set for the same value. If you want to change it, there's a pull down window. This is a good typical speed. Sometimes you may want to go a little bit faster, but this one's fine. And so on line 10, what we're telling the program is that the green LED, and like I said, if you hover over the name, it tells you it's on pin 8, red LED is on pin 9. But here we're telling the software to make that pin an output pin. They all default to input, but when you wanted to make it an output, it has to be defined. So that's what that's doing. Line number 3, it tells it that if you don't have a pull-up resistor on pin 3, you can add it in software. But in this case, I've commented that out because in hardware, I have that. And pin number 5 is going to be my pulse width modulation register. It's 8 bits wide and has a range of 0 to 255. Then I'm starting my main loop right here. The first line, I'm reading the analog input. I'm saving the register value to a variable called A0 integer, okay, which is right here. And the analog input register is 10 bits wide and has a range of 0 to 1023. Line 17, I'm reading the voltage and converting it. So here it is as an integer value, but I'm converting it to a voltage by dividing by 1023 and multiplying by the supply voltage. In my case, that's 4.6 volts. In this example, if the A0 integer register is 600 and I've adjusted my variable resistor so it is equal to 600, I would do the calculation of taking 600, dividing by 1023 and multiplying by 4.6 volts to get 2.7. That's my first column. And then I'm going to calculate the pulse width modulation value by using the map command. Okay. And if I have a value of 600, I would take the 600 divided by 1023, multiply it by the span. In this case, 230 minus 102 is 128. So the span is 128. And then after do the multiplication, I add 102. And that will give me a value of 177. Line number 19, I'm calculating the duty cycle. And the duty cycle in this case is the 177 divided by the 255 and then multiply by 100 to get it in percent. And in this case, the duty cycle is 69%. On line number 20, I'm trying to calculate the volts out of my low pass filter. And I'm doing that by taking the duty cycle and multiplying it by the supply voltage. So in my case, it's 69% times the supply voltage, which is 4.6 in my case. Okay, and then that gives me 1.41 volts. And then the time high, well, the pulse width modulation signal on pin 5 operates at a frequency of 490 hertz, and 1 over that is 2.04 milliseconds. So 69% times 2.04 milliseconds gives me the 1.41 milliseconds. And then I write that out so that it produces a waveform, and I can open up my picoscope to see that waveform. Okay, and it should show you here that the positive duty cycle is 69%, and if I multiply that voltage, as I mentioned, you're getting about 3.2 volts. You see that I'm measuring that here, and by measuring the top voltage of B, which is down here. And so all of those things make sense. So let's go back to the program. And we were here in the program, and what we're doing here is checking to see if the duty cycle, this number here, is between 40 and 50%. If it is, turn on a green LED. If it's not, turn off the green LED. And then the next line, 29 to 32, do the same thing, but checking for 80 to 90%. This double ampersand symbol means we're ANDing the first number 80 and 90 to see if it falls within that range. And then all of these are my serial monitor output commands. So I'm printing A0 integer, tabbing over, printing the V in with 2 decimal places, then the pulse width modulation, then my volts out, and this is my push button. I'm just going to press it on my board and see it goes to 1 when I press it. And this is my calculated supply voltage, calculated time high, the duty cycle, and then I have a 250 millisecond delay, and then I repeat it over and over again. So understand what each of these columns represent. Make sure your push button works. The other thing I'm going to try here is I'm going to set it to 40%, which is my minimum. The green LED comes on, and I go to 90%, the red LED comes on. The red LED will be on anywhere from 80 to 90, and the green will be on anywhere from 40 to 50%. Here I'm just scrolling through all of the possible values that you can maybe try them out, realizing that I have my voltage set to 4.6 because that's what I measured. I'm just going to come back down here. When you are doing the screen capture, it's probably a good idea to have this up on the screen. And so right now I have my slider or variable resistor turned fully clockwise. And that's why I'm getting 0 integer value, 0 volts. But because of my, let's see if I can find the map command here. Because of the map command, my minimum is 102. When I go all the way to 1023, I get 230. And then in between, I have a range of values. And you can see that the duty cycle here ranges from a minimum of 40 to a maximum of 90. Same thing for the voltage, 0.82 is the minimum output voltage. Or, sorry, that's actually, this is the actual voltage, and this is the time for the duty cycle. So if I go over to my picoscope, you're going to see that it's about 40% and 0.8 milliseconds. And then if I go all the way to the maximum, which is right here, my time high is 1.8 milliseconds. So it ranges as I move the slider back and forth. And in my software, so just to make it very clear, this is the actual output voltage, this is the supply, and this is the time high in milliseconds. So if I have a 50% duty cycle, let's try to set that up here. Okay, 50%, the time high is half of the period of the signal, which is 1.02. So I hope this short demonstration helps out. I'll be adding more videos, so it's a good idea to keep checking to see if there's an update, and you can subscribe as well to make sure that you're getting all the other videos that I might post online. Bye for now. This is an example of using the serial plotter. So to start with, you have to have program code that will create the plotter output. And what I've done here is I'm reading the analog input from A0, just a voltage from a variable resistor. I'm converting it to a real value by reading the integer value, dividing by 1023, and multiplying by the supply. And I measured the supply first, and I'm using it in the program. So the first two lines in the serial print set the Y limit. The next two lines set the minimum value for Y. And then the third line prints out the value and is going to print it out with 1 decimal point of precision. So that's why you see the value down here in the serial monitor of 5 volts, 0 volts, the minimum, 5 is the maximum, and the output voltage right now is 1.6. To start the serial plotter, come up to here, click on serial plotter, and I find turning on the interpolate button helpful, so I'm going to turn that on. And then I just move the variable resistor back and forth, and you're seeing the voltage appear on the plotter. Very useful for when you're working with different sensors. So I've got a minimum, maximum. The other thing is I want to speed this up. Each of these numbers represents a sample, and I'm operating at a very high speed here, 115,000 bits per second. Now make sure that the number you see down here matches up with what you've put in your program. I can change it to 9600. I'll do that right now. And I'll change this to 9600. One more right there. And now when the two of them are set to the same speed, it'll work okay. If you find that you're seeing these odd symbols, it's because you have to download the program again with the correct speed. I'm doing that right now. And now the numbers that you see here are correct, and the serial plotter appears here. It's a little bit slower because of my baud rate being slower. That's how it works. If you found these videos useful, please subscribe to the other videos I have online. Thank you.